So thus far in this class, we have been synthesizing dyads which have allowed us to put them together and form 4-bar mechanisms. Now, one thing that you're probably interested in is how do I get beyond a 4-bar, when's it appropriate, and how do I form these more complex mechanisms? That's what we'll focus on here when we talk about multi-loop mechanisms. And you'll see why we talk about it as multi-loop in just a moment. So before we even go there, why would we want to extend beyond a 4-bar? Very often a 4-bar mechanism is completely sufficient for majority of mechanical engineering tasks. In 3 precision positions, we have a huge amount of flexibility. We have 2 infinities of solutions, in other words, 2 free choices. I can make use of those to pick a motion generator with prescribed timing, meaning I'm prescribing what the rotation of the input link is, those beta 2 and beta 3 free choices. Alternatively, we'll learn later on that I can use those free choices to pick the location of my ground pivots and do ground pivot specification. So I have quite a bit of flexibility with 3 precision positions. Very often, as we move on to 4 or 5 precision position problems, we start to run into limitations. We no longer can do motion with prescribed timing because with 4 precision positions, we only have 1 free choice, and so I can't prescribe all the rotation angles. And these limited free choices, they can sometimes set up ground pivot or moving pivots in undesirable locations, as well as create mechanisms that are poorly behaved. I might have bad transmission angles, bad mechanical advantage, and I really don't have as much flexibility as I might like. I might not be able to fit all the ground pivots within the frame that I have. Whatever it is, I might have some limitations. And in some cases, we need more complex motion. We need longer reaches within for a mechanism that's relatively compact. I might need a more stable mechanism. Sometimes there are just limitations for a 4-bar. And that's when we say, let's move on to a multi-loop mechanism, which might be a 5-bar mechanism or a 6-bar or an 8-bar, depending on what we're interested in. We're going to focus on 6 bars in this lecture, but recognize that this approach is extendable. So the first multi-loop mechanism we're going to synthesize is a Watt 2 6-bar, where we're interested in a motion generation with prescribed timing. Now the motion that we're going to be creating is precision point 1 to precision point J, and this could be through 2 positions, 3, 4, 5, whatever it happens to be. And because it's motion, we're also concerned about the rotation of our coupler, which would be this phi angle right here. So let me grab a pen and we're going to prescribe the rotation phi. And then because we're prescribing the timing of the mechanism, the input or the rotation of an input link, that would be this angle psi down here. So we're prescribing all of that information. Now I want to synthesize this mechanism through however many precision positions, and I have multiple vector loops that I need to create here. We're going to solve each one of these vector loops separately, just like we did with a 4-bar mechanism where I solved the W and the Z, and the W star and the Z star. I solved them separately and then put them together. We do the same thing here, except I'm going to have 3 different vector loops, or sets of vector loops that I will solve simultaneously. We're going to find the order matters. I'll talk about that in just a moment. So first of all, let me form loop 1. And where this loop 1 is going to come from is I'm going to start at this ground pivot right here, come up to this moving pivot, and I will call that the Z2 vector. So that'll be Z2. And then going from that moving pivot up to the precision point, so this would be very similar to a W and Z that we would normally have. I'll call that Z3. That will take me up to the precision point. And then I have, going from precision point 1 to precision point J, I'll call it delta J. So I've got those vector loops, and I can talk about them in the first position as well as the jth position. And so I can then write this vector loop equation where I have Z2 times, in parentheses, its rotation operator, e to the I theta j minus 1. And then I'm adding that to Z3. And I've got its rotation operator, e to the I phi j minus 1. And then that's equal to the displacement vector, delta j. So this would look very much like any other motion with motion dyad that we would have, where I'd have W and Z, and in this case I've just renamed them as Z2 and Z3. That'll be my loop 1. Now loop 2 is going to be taking me up the other side of that base 4-bar, I'll call it, where I will be going from the other ground pivot up to this moving pivot, and I'll call that Z4. From that moving pivot up to the precision point, I'll call that Z5. And then I've got the same displacement vector going from precision point 1 to precision point J. So this loop 2 here, I will have Z4 multiplied in parentheses by its rotation operator, e to the I beta j minus 1 plus z5 times its rotation operator, e to the I phi j minus 1, and this is then equal to the same displacement vector, delta j. I would solve each one of these individually, so sequentially. I'd solve loop 1, create a solution for it, and then I'd solve loop 2. So on this third vector loop, we're going to start at the ground pivot z, and we're going to we'll have z6 multiplied by its rotation operator, e to the I psi j minus 1. We'll have then z7 times its rotation operator, e to the I gamma j minus 1. And then I could subtract off z8. Alternatively, I can throw it to the other side of my equation. And so I'm going to say this is then equal to z8 times its rotation operator, e to the I theta j minus 1. And this then gives me a nice system of equations. And you might say, well, why did you do it that way? What I want to do is I want to force each one of these into what we consider our standard form equation. Now in our standard form equation, we have everything on the right side of the equation as knowns, and on the left side of the equation, I have unknown vectors, so the w and the z equivalents, and one of my rotation angles is unknown. So let's go back through here and kind of say what's known, what's unknown. Now, let me go ahead and change colors here. So let me grab a blue here. Now, in my first vector loop equation, remember this is a motion generation problem, I have as prescribed variables, I've got the displacement vectors, and I also have the rotation of the coupler, which is the phi angle. So in that case, I have to go ahead and, in 3 positions, I would go ahead and pick values of the theta, and then I would generate and solve for z2 and z3. As I go to loop 2, I would say, all right, again, it's a motion generation dyad where I have a displacement vector as well as a rotation of my coupler. And now, very similarly, I would make in 3 positions, I would do free choices of my beta angle, and then I could solve for z4 and z5. Now, once I get down to this last loop, this is a function generation loop. Why is it a function generator? I'm only concerned about the rotation of the input link relative to the rotation of the output link, or the rotation of z6 relative to z8. Now, just like we talked about with a function generator in the past, I picked that w star vector, or the output link magnitude and initial angle. So I'm going to go ahead and pick z8 here. Prescribed as part of the problem, I've got the rotation of the output link, the theta, as well as the rotation psi as prescribed. So now I look on the other side of my equation, the left side of my equation, I have unknown z6 and z7, as well as the unknown rotation angle. So in 3 positions, I would go ahead and pick that rotation angle to give me the solutions for z6 and z7. If I didn't like the final solution for z6, z7, z8, I could then rotate and scale that last function generator to get it in the position I wanted to. So again, I would synthesize each one of these vector loops independently and then put them all together at the end and form this full 6-bar Watt-2 mechanism. So I've mentioned that the order is important. Let me now talk a little bit more about why that is. So because we're synthesizing each loop independently or individually, we need to pay attention to the order because in some cases, by synthesizing one part of the mechanism, it will then define the rotation of another vector. So our multi-loop plan of attack here is to first of all synthesize the simplest loops and move to the more complex loops. So we start with the dyad loops first. Then we move to the triad loops where we know the most about them, what's the most prescribed or known variables for some reason. And then we want to save our function generator loops for last because they're rotatable and scalable, and we can often use that to get it to fit within the mechanism. So we've done a Watt-2 example. Let me do one more example of a Stephenson 3 to apply these rules of thumb, or this plan of attack, if you will. So now I've got a Stephenson 3 where I'm interested in doing motion generation with prescribed timing. Now the precision point, I've got P1 up here, which is moving to P3, and the timing that I am prescribing is that psi angle that's on the bottom left. That is what I want to synthesize. So now I've got a displacement vector that takes me from position 1 to position 2. I'll call that, again, delta j. And I want to start off with my dyad loops first. Now, how do I get up to that precision point P1 with a dyad loop? Well, I can start at this location right here, and I can call that my z2 vector. and then I can go up to the precision point P1 with Z3, and I can call that loop 1. So loop 1 will be, in standard form, I'll have Z2 times its rotation operator, e to the I phi j minus 1, and then I'll add to that Z3 times its rotation operator, e to the I gamma j minus 1, and then that's equal to the displacement vector delta j. So that is now a standard form equation where, because it's a motion generator, prescribed as part of this problem is the rotation of the coupler. So that is prescribed, as well as the displacement vector. Both of those are prescribed. And then left on the left side of the equation are two unknown vectors, z2 and z3, as well as an unknown rotation, which is the rotation of the input link. So in this case, if it was 3 precision positions, I would go ahead and pick that value. Let me move on to a second loop. Now, my second loop, I have to pick it a little bit arbitrarily, but I want to go with the triad loop that I know the most about. So my two options are to start at either one of these other ground pivots and move up. Now, because I'm prescribing timing of the one on the very left here, I'm going to start there because I have the most information known about it. So loop 2 will be starting right here, moving up to that point, and I'll call that Z4. Then I'll have Z5 coming up to the top of this other kind of base 4 bar, if you will. And then Z6 will be taking me up to my precision point. So that's the triad that's taking me up there. So loop 2 will be a triad loop that I know the most about. So I've got Z4 times its rotation operator, e to the I psi j minus 1. And then I add to that Z5 times its rotation, e to the I beta j minus 1. And then, because it's a triad, I'm going to add Z6 to this times its rotation operator, e to the I gamma j minus 1. And then this will be equal to the displacement vector, delta j. Now, I had previously said that I want to take all of these vector loops and put them into what we call standard form. Now remember, standard form, I've got only 2 vectors on the left side and everything on the right side is known. And so right now I've got these 3 vectors with the parentheses components on the left side. I can only have 2. What I'm going to do is I'm going to go ahead and pick one of these vectors, and then I can move that over to the right side of my equation and then solve for it. So if I go ahead and pick Z6 and stick it on the other side of my equation, now I can force this into standard form where I have Z4 times its rotation operator of e to the I psi of j minus 1 plus Z5 times the rotation operator e to the I beta j minus 1. I'm throwing everything else on the other side of my equation, and I'm actually going to call it delta j prime. You'll see why in just a moment. But this will be equal to the initial delta j and subtracting off Z6 times its rotation operator e to the I gamma j minus 1. So now what I have done is I've put everything on the right side of my equation is known, and I've got only these 2 vector components on the left side, so I can now have this in standard form. So this delta j prime, that is basically saying if I have this point right here, where is that thing moving in space? It is basically a displacement vector for this point right here, which I'm writing in terms of the original displacement vector and Z6. So I'm lumping those together and saying, where does this point move as the precision point up here goes from position 1 to position j? Where's this point going to go? And that's the delta j prime vector. So if I wanted to add that in there, I could and say that arbitrarily might be something like this, where that would be delta j, let's see if I can get that, delta j prime. All right, so now I have that in standard form, and to solve this, I can say I have my rotation of the input link as prescribed, as well as delta j is prescribed because I already picked Z6, and the rotation of the coupler, gamma, this was already prescribed as well as part of the motion generation problem. So I went ahead and picked Z6, so everything on the right side of the equation is known. So I can then go ahead and solve for Z5 and Z4 if I pick a value for my beta j. So that's how I would solve that standard form dyad equation. It used to be a triad that I forced into a dyad standard form. All right, I've got one more vector loop. I'll call this loop 3. And this will take me from my other ground pivot up to this point. This will be Z7. And then I'll have Z8 up to here. And then to get up to the precision position, I simply have Z6 that I've already drawn. So my loop 3 here, I'll have Z7 times its rotation operator, e to the I theta j minus 1 plus Z8 times its rotation operator, e to the I beta j minus 1. And then just like I did before, I'm going to throw everything else on the right side of the equation, and I'll have delta j prime. This is the same one that I had in the loop 2. And this is equal to delta j minus the z6 times its rotation operator, e to the I gamma j minus 1. All right, so we're on to this last vector loop, and I want to solve this. I know everything on the right side of my equation. This is all known, so I'm set there. Now, what about the left side of the equation? Remember, one of these rotation angles I want to have as a known, and I want to pick the other one. Now, the reason that the order was important here is because when I solve loop 2, remember that I made free choices for beta j. And because I made free choices for beta j, and because I picked beta j, that free choice has to be the same as goes into here. So basically that information has already been picked in loop 2. So I have to use that same information in this loop 3, and that's why I saved it for last. Because now, if I go ahead and use that same information, now I can pick values for here, for the theta angle, and then I can solve for Z7 and Z8. So I had to solve loop 2 before I solved loop 3, and that's why the order is important. Now, very similarly, we can often save that function generator for last if I had a function generation loop, which I don't here, but I would save that for last because often that is influenced in a similar way. So again, these multi-loop mechanisms can vary drastically. They can be any of the Watts or Stevenson configurations. We can extend them out to geared 5 bars or even 8-bar mechanisms. But generally, we want to condense these back down into the standard form equation, which then we can solve using the same codes that we've written for our 4-bar mechanisms, our dyad equations. It makes it very easy to do. And the processes that we've learned for 3 precision positions apply, what we're going to learn for 4 precision position synthesis applies, and we can apply all of those to the standard dyad form equation.